Hello and welcome to lecture 21. So, in last lecture we were discussing about the numerical, where we have discussed about the 2-spool turbojet engine with afterburner, and we were discussing about the ground condition. So, parameters what we have selected are, say, compression ratio of LP spool, that is 3.35, compression ratio of HP spool, it is 4.65, turbine entry temperature we have considered 1200 Kelvin, air mass flow rate we have taken 186. Let us consider for that it is a sea level condition, ground condition, so atmospheric condition, that is what is our inlet condition. And here in this case we are considering, say, our afterburner, it is operative, and the afterburner temperature we have considered as, say, 1700 Kelvin, and there is 5% loss and 95% of efficiency for this afterburner. So, if we go through what all we were doing is in terms of calculation of exit pressure and exit temperature from different components. So, we have done our calculation based on, say, exit temperature and pressure of intake, exit pressure and exit temperature of LP compressor, exit pressure and exit temperature for, say, HP compressor. We have done calculation for turbine entry temperature with the pressure and fuel air ratio. We also have done calculation for exit pressure and temperature for LP turbine and HP turbine. Since we are having, say, afterburner, and that is the reason we have done the calculation for, say, fuel air ratio for the afterburner, since the temperature it is known to us. Then we have done our calculation for the nozzle, and based on critical pressure we have found, like our nozzle it is a choke nozzle. So, my exit pressure it is my critical pressure. So, up to that we have done calculation in the last lecture. Let us move ahead with the calculation of the performance parameters. So, if we recall the performance parameters like thrust specific fuel consumption, different efficiencies like propulsive efficiency, thermal efficiency, overall efficiency, we will be calculating for this numerical. So, let us move here. Say we have our thrust equation, that is given by m dot infinity into 1 plus FAB V9 minus V infinity. Let us recall, since we are having our afterburner it is operative, that is the reason why this formulation it is different from inoperative of afterburner. We will be having FAB, that is in multiplication of V9, and here this is my pressure thrust, it is P9 minus P infinity into A9. So, if we look at this M infinity number that is given to us, F and FAB we have calculated, V9 also we have calculated in last lecture. Now, P9 and P infinity, that is what is also known to us. The unknown parameter here it is my area, say area of my nozzle or nozzle exit area. This nozzle exit area, as we have done calculation for the previous cases, that can be correlated in terms of, say, mass flow rate. So, if we will write the mass flow rate, it is given by m dot equal to density into area into velocity. Now, since my mass flow rate it is the combination of mass flow rate of air plus what amount of fuel we are injecting in our combustor, the amount of fuel we are injecting in afterburner. So, we need to be careful here in terms of calculation of the exit area. So, here in this case again this density at the exit it is not known to us, but what we know is our pressure and temperature. So, let us put that number, it is given by P9 by RT9 or RT9A. Now, here we know what is our pressure, as we have discussed, my exit pressure it is equal to, say, my critical pressure. Now, if we will put this number, my density is coming 0.2728. Now, once the density is known to us, we can calculate what will be our area. So, if we will be putting our mass flow rate, F value, FAB value, our exit velocity and our density, then area is coming 0.9574 meter square. So, this is the area of nozzle at the exit. Since now A9 is also known to us, we can straightway put this value in our thrust equation. So, for the thrust equation, we know all these parameters. So, let us put these numbers, say M infinity is 186, F 0.0168, FAB 0.026, exit velocity is 742.66, and since this is my ground condition, so V infinity equal to 0. This pressure we have done the calculation, my atmospheric pressure is known and area we have calculated. So, this thrust it is coming up 157.8 kilonewton. Now, our next important parameter it is thrust specific fuel consumption. So, this is given by m dot F divided by thrust. This m dot F here in this case it will be m infinity into F plus FAB, because here we have the operational afterburner. So, that is also consuming the fuel. So, we need to be very careful in terms of putting this equation. So, if we are putting these numbers, my thrust specific fuel consumption it is coming 0.05045 grams per Newton second. Okay. Now, let us move towards the next step. Our next step it is to calculate the propulsive efficiency. This propulsive efficiency we are writing in terms of thrust into my free stream velocity. Here in this case my velocity it is 0. So, my propulsive efficiency will be coming as 0. The thermal efficiency we are correlating in terms of my kinetic energy as well as in terms of my say thrust power T into V infinity divided by the amount of fuel we are inputting. So, if we are putting all these numbers, then our efficiency it is coming as 14.93%. Now, important parameter for us is overall efficiency, or we can say thermopropulsive efficiency. Since my propulsive efficiency is 0, so overall efficiency that is coming as 0. So, this is the way in which we are calculating our parameters, performance parameters. We need to be very careful in terms of selection of fuel air ratio. Okay. Now, let us move and let us try to put this in our understanding. So, here in this case we can say we have done our calculation for the net thrust, we have done calculation for thrust specific fuel consumption, thermal efficiency is coming 14.93, propulsive and overall efficiency that is 0. Now, if you recall in week 3 we have done the calculation for 2-spool turbojet engine, and that too it is without afterburner. So, purposefully that numerical we have solved in week 3. Those who have not gone through, just refer week 3 the numerical for 2-spool configuration, that too it is for our ground condition. So, if we compare, then we will realize here in this case with the operational of afterburner, the exit area is coming to be higher. My thrust, net thrust that is also increasing, thrust specific fuel consumption also is increasing, but at the same time our thermal efficiency is going down, because more amount of fuel that is what has been consumed by our afterburner. So, let us try to recall what all we have done in terms of this calculation. What all we know is we want to understand the effect of different parameters on the performance. So, we say our performance parameters are like thrust, thrust specific fuel consumption, fuel air ratio, propulsive efficiency, thermal efficiency, overall efficiency, and we know our cycle parameters which are affecting on this performance are say compressor pressure ratio, what we say overall pressure ratio. We can say here since this is 2-spool configuration, so we will be having LP compressor pressure ratio, HP compressor pressure ratio. By changing one of the pressure ratio, we can increase our overall pressure ratio. The important parameter we have is turbine entry temperature. We have different components, they are having their own efficiencies like diffuser, compressors, combustion chamber, turbine, nozzle, afterburner, they are having their own efficiency. those efficiencies also have impact directly on the performance parameters. We have this as our ground condition. We can go with say flight condition also, that is what we will be discussing in next lecture. We are having afterburner temperature. So, the effect of this afterburner temperature also need to be realized. We can have our flight condition. Under that flight condition, what will be the flight speed, that also has impact on the performance parameters. So, let us try to select one by one. Very first parameter we are selecting is the effect of LP compressor pressure ratio. For this we are putting HP compressor pressure ratio and turbine entry temperature TIT or TET to be constant. So, very first parameter let us take, it is my LP pressure ratio, LP compressor pressure ratio versus thrust, and here by putting my HP compressor pressure ratio constant and by changing my LP compressor pressure ratio, overall pressure ratio, that is what is going to be changed. And here if we look at, this is our design condition. It says when we are increasing our LP compressor pressure ratio, our thrust is reducing. It means by increasing my overall pressure ratio, we are reducing the thrust. So, if you recall in week 3, we were having the discussion about this parameter. So, if we plot our TS diagram and for fixed turbine entry temperature, we can say by increasing our pressure ratio, we are moving more towards the left hand side, and that is what is putting the constraint here. We will be having our V9 to be lower, that will be impacting on my P9, and in overall sense we can say our thrust, that is what is going to be reduced. Say next parameter what we have is my specific thrust. This specific thrust we are correlating in terms of thrust divided by M infinity. This M infinity is my entry mass flow rate. Since my thrust is reducing, so my specific thrust, that is what is going to be reduced. Now, the parameter what we know is say thrust specific fuel consumption. This thrust specific fuel consumption, as we have discussed, it is a function of my amount of fuel which will be consumed or we will be supplying in combustion chamber and the amount of fuel we are supplying in the afterburner divided by my thrust. Here in this case, since we are increasing our say compression ratio, we can say in order to achieve same temperature, the amount of fuel required to be supplied, that will be lower, because we need to raise temperature by small amount. At the same time, if we look at in denominator, since we are having thrust value, that is what is higher, and that is the reason why our thrust specific fuel consumption, that is what is going to be increased with increase of LP pressure ratio. Now, let us look at what is happening with our efficiency. Since this is we are discussing about the ground condition, that is the reason we will not be having our propulsive efficiency and overall efficiency, that is coming into the picture. Here it is interesting to observe, if you look at, this is what is representing my design condition, my thermal efficiency, that is what is remains nearly constant for particular pressure ratio, and then after the efficiency is reducing drastically. So, we can say our overall pressure ratio, that is what is having great impact on our thrust as well as on thermal efficiency. This is what is discussed for particular turbine entry temperature, be careful. Now, let us look at what is happening if we will be increasing our HP compressor pressure ratio. For that, we will be putting our LP compressor pressure ratio and turbine entry temperature to be constant. So, in line to what all we have discussed for the previous case, since my overall pressure ratio is increasing, the thrust is going to be reduced. Same will be the impact on my specific thrust, similar to what we have discussed for increase of overall pressure ratio by changing my LP compressor pressure ratio, specific fuel consumption, that will be going to be increased here. Let us look at what is happening with the efficiency. So, for efficiency also we will be having similar effect. So, we can say the selection of this LP compressor pressure ratio and HP compressor pressure ratio by variation of these pressure ratios, and if we are changing our overall pressure ratio, we need to be very careful about what turbine entry temperature we are expecting to be achieved. So, this is not the general case. Here in this case, we are considering turbine entry temperature to be say 1200. Suppose if I consider my turbine entry temperature is 1400, these plots will be different. Suppose if I consider 1600, my plots will be different. So, you cannot say this as a generalized case. So, let us try to look at what is happening with my turbine entry temperature. So, here in this case we will say effect of turbine entry temperature, we will be putting our overall pressure ratio or LP compressor and HP compressor pressure ratio to be constant. So, in this case if we look at by increasing the turbine entry temperature, we are increasing our thrust, and reason we can clearly see this increase of turbine entry temperature that has impact on my exit velocity as well as on my exit pressure, and that is what is coming to be higher, which will lead to increase the thrust. If we consider our specific thrust, since it is in direct proportion with the thrust, we can say with increase of thrust, the specific thrust also is going to be increased for particular mass flow rate. Now, here in this case, the reverse trend we can say we are observing by increasing the turbine entry temperature and putting the pressure ratio to be constant, our specific fuel consumption that will be reducing. So, one of the way in terms of looking for reducing the specific fuel consumption, it says for particular pressure ratio we need to move with the increase of turbine entry temperature. So, we will be discussing this in detail, and we have earlier also discussed the reason why people they have moved from lower turbine entry temperature towards the higher turbine entry temperature. And we also have realized it is not the number, we need to be careful about the material of our turbine blades. It may not sustain very high temperature because of metallurgical constraint, and that is what is putting our limit in terms of turbine entry temperature. Let us look at what is happening with the thermal efficiency. It says if we are increasing our turbine entry temperature, we will be having say thermal efficiency to be higher, and that is what is coming to be constant. So, on lower side also if we look at, we can say if we are having turbine entry temperature to be lower, we will be having our thrust to be lower, we will be having higher thrust specific fuel consumption, our thermal efficiency also will be lower. So, we need to be very careful in terms of selection of this number. So, we are discussing about the thermal cycle analysis for two spool configuration. By this calculation, by these plots, one can easily understand what need to be the numbers for the pressure ratio, what need to be the number for turbine entry temperature, and how it will be impacting on our performance parameters. Now, let us look at say afterburner exit temperature. So, here we are putting our turbine entry temperature, LP compressor and HP compressor pressure ratio to be constant, and in this case it says if we are increasing our afterburner temperature, this is our design condition, it is 1700 Kelvin. If we are increasing our afterburner temperature, we can say we are able to increase the thrust. Suppose if we are moving towards the lower side, we can say we can have the thrust to be higher compared to what all we are looking for in terms of without afterburner, but this number will be lower. Be careful, this cannot be equal to the turbine entry temperature. Okay. Now, here in this case, this is representing my specific thrust. We have our next parameter, that is say specific fuel consumption, thrust specific fuel consumption, and in this case we can say since we want higher temperature for the afterburner, that means the amount of fuel required to be injected in afterburner will be larger. Though we are having my thrust to be higher, but the amount of fuel that's required for afterburner is huge compared to the rise of my thrust, and that's the reason why we are having our thrust specific fuel consumption that will be increasing. So you can understand what is the reason why we are operating our afterburner for a small duration. Okay. Now let us look at what is happening with the thermal efficiency. With the increase of afterburner temperature, the thermal efficiency is going to be lower. The reason is clear. Here the amount of fuel required in the afterburner will be large. Okay. And let us look at what is happening with the nozzle area. Since we are increasing our turbine entry temperature, the amount of the fuel that is added in afterburner will be large, and that is the reason why in order to handle that large mass flow rate, the area requirement also will be large. Okay. Now here in this case, let us look at what is happening with my air flow rate. So this is representing if we are increasing the air mass flow rate at the entry, our thrust, that is what is going to be increased. Same way if we look at in terms of specific fuel consumption, it has not much impact because the amount of fuel what we are adding in afterburner and amount of fuel what we are adding in the combustor, it has not major effect because of change of this mass flow rate. And this is representing our thermal efficiency that also remains nearly constant. And here in this case, in order to handle that large mass flow rate, we need to have our nozzle area to be large. So this is giving very good idea in terms of what all is the impact of the parameters called pressure ratio, turbine entry temperature, the effect of say afterburner temperature, and the effect of this mass flow rate. Okay. Now let us look at the new idea what all we have discussed up till now in last numerical, that is afterburner it is operating, but that is what is at the ground condition. And let us try to solve the same numerical considering the flight condition. Let us say this engine it is fitted with the aircraft which is flying at Mach 2.04 at 8000 meter altitude. The temperature and pressure at that location is say 236.23 Kelvin and pressure is 36.651 kilopascal. So be careful when we are talking about the flight condition. Under that flight condition my altitude is changing, and because of change of altitude my entry temperature and my entry pressure also will be changing. Let us solve same numerical considering say afterburner is operative and we are considering say the temperature at the exit of my afterburner, it is say 1700 Kelvin. Okay. So let us try to understand what all we will be doing here. Since this is what is my first component as intake diffuser, I am having my flight condition and that flight condition has impact on my say exit pressure and exit temperature from the intake. We will be doing the calculation for say exit temperature and exit pressure of LP compressor. We will be doing our calculation for exit pressure and exit temperature for HP compressor. We have our combustion chamber. For that maximum turbine entry temperature it is given to us. So we will be doing our calculation for fuel air ratio. Our temperature is known to us. We can calculate what is my exit pressure from the combustor. Then we will be doing calculation for the HP turbine. We will calculate my exit pressure and exit temperature from the HP turbine. Similar to that, we will be doing calculation for the LP turbine. We will do calculation for the afterburner, and for afterburner maximum temperature it is given to us. We will be doing the calculation for exit pressure and temperature from the afterburner. Then we have last component as a nozzle. For the nozzle we will be doing calculation for the critical pressure. Based on that, we will do calculation for our exit velocity, and from this exit velocity we will try to calculate our performance parameters. So this is how we will be solving this numerical. So let us try to move forward. So very first component here is say our intake. Since we are having our entry Mach number, it is 2.04. So here in this case we can do our calculation for say flight speed, that is m infinity into square root of gamma r t infinity. Let us put this number. By putting this number, it says my flight speed is 628.5 meter per second. We have our definition for the diffuser efficiency, and based on that we can do calculation for the exit pressure. Since here in this case we have our entry Mach number, it is known. So we will be putting this number here. My free stream pressure is 36.651 kilopascal. We have diffuser efficiency 90% and flying Mach number 2.04. So it says the exit pressure is coming to be 259.37 kilopascal. So by this way we can calculate our total pressure at the exit of the diffuser. We know this process as a adiabatic process. Here in this case we will do our calculation for the exit temperature, and this exit temperature it is coming 432.85 kilopascal. Okay. Now here in this case let us try to do the calculation for LP compressor. Say for LP compressor pressure ratio is given 3.35. We can do our calculation for LP compressor exit pressure. So this exit pressure is coming 868.9 kilopascal. Since we know our efficiency, so based on that efficiency we can correlate efficiency and pressure ratio to calculate the temperature ratio. So based on that we can do the calculation for the exit temperature. Since my pressure ratio is 3.35, compressor efficiency is given 88%, T02 we have calculated from the exit of our intake. So it says my temperature is coming 635.79 Kelvin. Similarly, we can do our calculation for exit temperature and exit pressure from the HP compressor. Here in this case the pressure ratio is given 4.65. So for that case, if we are putting exit pressure calculated from the LP compressor, we will calculate the exit pressure from the HP compressor, and that is coming 4040.39 kilopascal. In line to what calculation we have done for the temperature ratio, here also we can correlate temperature ratio in the form of compressor efficiency as well as pressure ratio. For this case here we know the pressure ratio to be 4.65 and efficiency is 88%. So we can calculate the exit temperature. This exit temperature is coming 1034.11 Kelvin. We need to be very careful about writing the units. Now we have our next component as our combustion chamber, and in that combustion chamber we have certain amount of drop of pressure. It says there is 3% drop of pressure. So we can say our exit pressure from the combustion chamber it is 3919.18 kilopascal. So here this is what is my mass balance. Let us try to put the energy balance here. So suppose if I consider this is my combustion chamber, this is representing my entry condition to the combustion chamber. This is the amount of fuel what we are adding with say burner efficiency or combustion chamber efficiency, and this is the amount of heat or energy that is what is leaving from the combustion chamber. And if you will write the energy equation, it gives me the value of F, it is mass flow rate of the fuel to the mass flow rate of the air. Since here in this case we know the value of Cp of hot gas, Cp of air, we know the turbine entry temperature, we know what is a combustion chamber entry temperature, and based on that we can do the calculation, and this is coming 0.0084. Okay. Now let us move towards the next component. So we know our HP turbine that is used to rotate our HP compressor, and their work we are correlating by the parameter called mechanical efficiency. So here I am writing the work for the compressor as a MCP delta T0, that is what is equal to, here in this case we need to be careful, my M that will be changing, it is M infinity into 1 plus F Cp of hot gas T05 minus T06. So if we are putting these values, since my turbine entry temperature is known 1200 Kelvin, we can calculate the turbine exit temperature as 796 Kelvin. Okay. In order to calculate the pressure ratio, we have correlation in terms of efficiency. So let us use this equation. It says my expansion ratio, that is given by 1 minus T05 minus T06 divided by our turbine efficiency into T05. Here if we will be putting these numbers, my exit pressure from the HP turbine, it is coming as 573.75 kilopascal. Okay. Now what next component we have is our HP, it is LP turbine. This LP turbine, it is used to rotate the LP compressor, and work we are correlating with the mechanical efficiency here. So let us put the work balance. Here for the compressor it is given by MCP delta T0, this delta T0 is 303 minus T02, and for turbine it will be T06 minus T07. So if we put all these numbers with mechanical efficiency to be 85%, we are getting LP turbine exit temperature as 590.16 Kelvin. Now let us move ahead with the calculation for the pressure. I am sure you are confident enough in order to calculate what will be my exit pressure from the LP turbine. For LP turbine also we can correlate our expansion ratio with the temperature, and that is what we are putting here. And if we put all this number, the exit pressure from the LP turbine, that is coming as 142.32 kilopascal. Now here in this case the exit from the LP turbine, that is what is going inside the afterburner. Okay. So let us consider the next component to be afterburner. It says there is 5% drop of pressure which is happening in the afterburner. So we can calculate the exit pressure from the afterburner, and that is 135.2 kilopascal. Now temperature T08, it is known to us. Okay. Here in this case we can say this is my mass balance, and in line to that we can write down our energy balance. Okay. Suppose if I consider this is my control volume, the amount of energy, that is what is coming out from say turbine, it is M infinity plus MF into H07. This is the amount of fuel what we are adding in the afterburner, and this is what is coming out from the afterburner. It is nothing but mass flow rate of air plus mass flow rate of fuel plus the amount of mass flow rate of fuel that we are adding in afterburner. So if we are putting the energy equation, it says this is given by say M infinity plus MF H07 plus say afterburner efficiency into M dot into CV, that is what is equal to this as my exit condition. Now, if we will try to solve this, and if we are putting all this number, we need to be very careful. This Cp value what we are putting, those all Cp values need to be in joule. Otherwise, we may come up with the number that is what is, say, maybe some different numbers, and that you cannot accept. Okay? So, be careful about these numbers. It says my fuel air ratio for the afterburner, that is coming as 0.0317. Okay. Now, the next component what we have is our nozzle, and that nozzle we know, for nozzle we need to check with whether the nozzle is choked or unchoked, and in order to do that calculation we need to go with the calculation of critical pressure ratio. So, here in this case we are correlating our pressure ratio in terms of nozzle efficiency. Since nozzle efficiency is given as a 96%, so if we are putting that number, we are calculating our critical pressure, and this critical pressure is coming as 71.8 kilopascal. Now, let us try to compare this value. If we look at my critical pressure, it is coming as 71.8 kilopascal. At the same time, at that flight condition, my P infinity given is 36.65. So, we can say our nozzle is choked nozzle, and for the choked nozzle we are considering our exit pressure as a critical pressure. So, we need to be very careful here. If we are making mistake here, that is what will lead to give the wrong value for the exit velocity, at the same time that will lead to give the wrong value for the thrust calculation. Okay. So, let us try to look at this. We want our exit velocity to be calculated, and that exit velocity is a function of the temperature. So, we will take the temperature ratio as the case. For that temperature ratio, we can calculate our static temperature at the exit of the nozzle, and that is coming as 1478.26 Kelvin. Now, what we know, our exhaust velocity, it is given by root gamma r T9AA. So, here just be careful what we are discussing about choke and unchoked nozzle. So, this is my atmospheric pressure, okay, and this pressure, that is what is slightly on the higher side, because our nozzle is a choke nozzle. So, if we are putting this number, it says the exit velocity is coming as 742.66 meter per second. Okay. So, this is what is for the calculation of all our cycle parameters at this moment. So, if we recall what all we have done for this lecture is, initially we have discussed for afterburner operation performance when we are considering the ground condition. Then we have taken the same numerical for the flight condition with the flying Mach number of 2.04, and we have considered our altitude as say 8000 meter. So, here we are stopping with. In next lecture we will try to discuss what all will be the performance parameter when we are considering the calculation for the particular case. Okay. Here in this case, now onwards we will be discussing for the comparison of our parameter in terms of how it is changing for the ground condition, how it is changing with the flight condition. So, thank you very much. I expect you to start doing the calculation for the performance parameter, do calculation for the thrust specific fuel consumption, do calculation for propulsive efficiency, thermal efficiency, overall efficiency, and just try to vary the performance parameter and try to plot the performance parameters, how it is changing with considering different pressure ratio, different turbine entry temperature values, different mass flow rate value, afterburner value, flying Mach number value, and that's what will be giving some great idea for detailed understanding. So if we try to understand here, now we are slowly moving towards the realistic condition and we are trying to move towards detailed understanding of turbojet engine. Thank you very much.